Hello, I'm Aaron Russell. I'm a junior at the University of Texas, majoring in geology with a minor in astronomy. I'm going to talk about a research paper that I recently read entitled Mars Sedimentary Rock Erosion Rates Constrained Using Crater Counts with Applications to Organic Matter Preservation and a Global Dust Cycle, written by Kite and Mayer from the University of Chicago. First off, understand that missions to Mars are incredibly expensive, and so our missions to look for signs of life need to be precise and well in place before launch. We can't just go rolling around Mars blindly with no idea on where to look for evidence. So a suitable location needs to be chosen where we think that we have the best chance of finding organic matter. Identifying a location was in part the objective of this paper. There are many types of organic matter, but complex organic matter is uniquely of biological origin. The problem with locating this type of organic matter is that it will be destroyed by cosmic radiation within 1 billion years due to the dissociation of molecules in a process known as radiolysis. But if the organic matter is buried a few centimeters, it can be shielded and has a greater chance of survival. The authors worked under the assumption that the burial of the organic matter was due to wind erosion. So, in order to calculate the odds of survival, they had to determine the rate at which erosion occurs in various places. However, there is only one proxy for wind erosion on Mars, and that is the size-frequency distribution of craters. The size-frequency distribution of craters can be used to determine the age of craters on the Martian surface. Once age has been determined, the ratio between diameter and depth can be used to solve for the rate at which the craters are being eroded. Within some locales, there are a subset of easily erodible rocks known simply as light-toned sedimentary rocks, where fewer smaller craters are present relative to larger ones. These areas and other locations where the potential for finding organic matter is high is where the authors decided to start counting craters and estimating age. A total of more than 13,000 craters were mapped over an area of 546 square kilometers. Erosion rates were then calculated for each location, as well as a global average of 100 nanometers per year. With the erosion rate, the authors were then able to calculate the probability of organic matter surviving radiolysis at each location. The Valles Marineris and Gale locations were calculated to have underwent 100 to 1,000 nanometers a year of erosion, and therefore about 65% of any complex organic matter surviving radiolysis. The southwestern area of Melas Chasma was determined to have about half of any complex organic matter surviving, but due to the belief that it was the site of an ancient lake makes this site a good destination for future missions. These results were calculated with fairly large errors. The analysts who counted the craters had a tendency to underestimate diameters and had a 25% false negative rate. When these errors were accounted for, erosion rates dropped by 30%, worsening radiolysis survivability potential. The crater flux models the authors used in determining age are based upon lunar models, and the authors conceded that if other calculations that have been given are correct, then this model would be rendered inaccurate. Realistic decay rates in Martian soil would also lower the survivability of complex organic matter by an order of magnitude, but at depths of 2 meters, survivability is greatly increased globally. Even though these results have quite a bit of error standing in the way of their conclusiveness, the authors did manage to determine that a fairly large amount of dust should cover the planet when using this rate of erosion. And because there is not a 4-meter global layer of dust, the authors can conclude that there must be dust sinks. So, due to the precise and costly nature of missions to Mars, we must determine locations where we think we have the greatest chance of answering the most amount of questions. The authors have given us an idea of where we may go next in order to answer these questions. And although we did not pinpoint an exact location, we did rule out a couple. And thus is the nature of science. I hope you enjoyed, and thank you for your time.